This is Turgeon, free fall tutorial. 4 things I'm going to talk about. Let's go. So first, the definition of free fall. Obviously, think of it as an object is falling, like you imagine the space ball falling, but here's a definition that's kind of a Turgeon definition, and you can picture it as there's an object that is subject to only one force, and that force is the force of gravity. Not sure why that arrow didn't come out, but imagine that this baseball does not have anything else acting on it except the force of gravity, so we are ignoring air friction, because if there were air friction, there would be another upward force going right here. Acceleration and velocity. Okay, there's a key question on your summary sheet that says something like this: what's the difference between acceleration and velocity? There's another key question that says describe the acceleration and the velocity of an object that's in free fall. So let's go. Let's say I drop this baseball and I'm going to draw the motion map. Let me do this kind of roughly and kind of incorrectly. If I start throwing in dots like this, you can see that doesn't make sense, because you know this thing is accelerating, so it ought to be picking up speed. So it starts from rest, it picks up some velocity, picks up more velocity by the end. Now I'm going to put these velocity arrows in, but again, if I put these velocity arrows in, these don't really make sense. They should not all be equal velocity arrows. So I'm going to make this final velocity arrow larger than the others, and I'll make the oh shoot, I gotta pause this. Sorry for my language there. I had to make it so that these arrows could change size. I need a small arrow on the first moment, slightly longer arrow, and then a longest arrow toward the end. Notice there's no velocity here. There's no velocity here. And the reason for that is, if you think about what's going on here, as time goes by, there's different moments happening here, and let's look at the time and the velocity. So this whole thing is under the influence of an acceleration that's downward. That acceleration is downward due to gravity, and it's g. It's 10 meters per second per second. And it's understood that this influence is happening the entire time. This is due to the force of gravity, so it's happening here, it's happening here, it's happening here, it's happening here. As soon as you let go of that baseball, this thing is under the influence of gravity and only gravity, so it has an acceleration of 10 meters per second for every second that passes. So what I'm going to do is I'm going to make a bunch of 1 second, 2 seconds, 3 seconds. Let's add a 0 seconds. Let's talk about what that means. As time goes by, the velocities are changing. They start at no velocity. They go to 10 meters per second. Think about this. The acceleration means as time goes by, the velocity is changing. No velocity. 10 meters per second, 20 meters per second, 30 meters per second. You can imagine that if I threw the object upward, it would be slowing down on the way up. Maybe it even comes to a stop. But the object would still have a downward acceleration the whole time of 10 meters per second per second. And maybe it has these velocities. But this doesn't make sense. It can't be. I said it was going up, so we would swing these around. This bothers people. How can it be going upward and have a downward acceleration? Well, that's the only possibility, folks, because this acceleration is saying that those velocities are decreasing. They're changing, because acceleration is a change in velocity. Those velocities are changing in that direction. Let's do some problems. Here they are. Pause the video, maybe try them yourself. Here comes the solution to number 1. if the baseball's dropped from that height, here's my motion map. I can see there's no velocity in the beginning. This height that's represented is from here at the top, here at the bottom, to the ground. Look at my information that I know. And here's the part where I think people really got confused. Here's the part where I think people really needed some help from the teacher, were having trouble understanding what's going on. You didn't know on the test that we needed to use this equation. Here's like this information. How did you know? What's up here? Well, how did you know to use this equation? How did you know from this information? It doesn't feel like there's enough. What's going on here? Well, one fact is that this is for free fall only. That equation is for free fall only. And by that equation, I mean this equation right here. So when I see a free fall situation and I want to find something out about it, and I'm given this distance, this is where you think, oh, okay, that distance right there, that's a free fall distance, so I'm going to use the free fall distance equation. Don't do random stuff where you're like multiplying by 10. We will multiply by 10. That's my next caution statement. So I do the algebra. You can see it all worked out here. And then I get my square root at the end. I get 2.6 seconds. And then I just jump to this and I go, okay, my answer is 26 meters per second. How do you know that? Careful. Don't just randomly multiply stuff by 10. The reason I knew to just multiply by 10 is I'm thinking about this diagram right here. I'm thinking about the 0, 1, 2, 3, and this relationship between time and velocity. But be careful. That's a relationship between time and velocity. It's not between distance and velocity. It's not between distance and time. It's related to the acceleration, though, right? So there's my 26 meters per second squared. 26 meters per second, I'm sorry. Now, there's another way to do this. Here's the algebraic way of doing it. You can identify all your knowns and unknowns, and I hope you can see the orange on the video here. I've got a new known, which is 2.6 seconds. I've got a new known where I'm writing down the original velocity is 0 right there. See that? Original velocity 0. Now I have a new unknown, which is the final velocity. If you look at a, t, v final, and 0, this equation makes sense. Plug in the numbers in red. First algebraic step is in blue, which is to multiply both sides by 2.6. You end up with this step, 26 equals v final minus 0. And you solve for that and you get 26 meters per second. Notice that the strategy here was the first thing I had to do before I can find the maximum speed is I got to get that time because of that time and velocity relationship. Where does that happen? Look at my picture. It happens at the very end, but careful, just before it hits the ground. And don't do this. Never draw that last point without an arrow. And never draw it right on the ground if you're drawing the ground. Another problem here. Pretty straightforward. This time, it's really obvious to use d equals 1/2 gt squared because you have a time. You're asked for the height, which you're supposed to think height, distance. You're supposed to know that g is 10. Boom, plug, chug, 45 meters. That's what I consider the easy version of a free fall problem. Now let's talk about something called terminal velocity. Terminal velocity is free fall with air resistance. Let's check out this picture that I found from physicsclassroom.com. This is a normal free fall situation. Someone just jumped out of a helicopter. They're going to have a parachute open, don't worry. But there's an 830 Newton gravitational force. But then air resistance starts to build up because you go faster. So now it's 350 newtons of air resistance. Still accelerating pretty quickly, but not accelerating at 10 meters per second squared anymore. The only place you're accelerating at 10 meters per second squared is here. Acceleration's decreasing even though your velocity's increasing. You're still getting faster and faster, but not as quickly. This is an acceleration of, say, like 6 meters per second squared, or maybe it's only like 2 meters per second squared. Now here we have no acceleration in this last case because the force of gravity is being canceled out completely by the force of air resistance. If you were to draw that as a motion map, it would look like this. Remember that first case where I was drawing a motion map and I was saying this something doesn't feel right here? Well, now it is going to be right. We're just going to do equal spacing, Think about the acceleration here. You're tempted to say that the acceleration it's in free fall, but don't memorize. Think about it. Free fall, this can't be an acceleration of 10 because it's not really in free fall. It's at terminal velocity. This is not accelerating at 10 meters per second squared. This is a constant velocity and 0 acceleration. Free fall and terminal velocity, the reason that's confusing is because it's not really free fall. It's terminal velocity. Terminal velocity is not the same thing as free fall, but it still kind of fits in that general category. What's that? Hold on a sec. Do you guys see that? Oh, it's a summary. I think I see a summary. Free fall is basically falling with no air resistance. And you're subject only to the forces of gravity. Acceleration and velocity in free fall, the thing is constantly accelerating. The velocity changes at a very specific rate, 10 meters per second, 20 meters per second, 30 meters per second. If it's going up, it's going to decrease, 40 meters per second, 30 meters per second, 20 meters per second, because of the 10 meter per second squared gravitational acceleration. We did some problems and we focused on when do I know to use the d equals 1/2 gt squared free fall equation. And finally, terminal velocity is kind of like an exception to the rule. It's not precisely free fall. It's when we look at a more realistic scenario of air friction operating.